So in yesterday's class, we were talking about uh, the reasons because of which the value of G may change. We have found that it will affect, it will change due to height, it will change due to depth. Clear. In today's class, we'll talk some more reasons because of which the value of G may change. Let's say there's variation in value of G uh, due to irregularities in Earth, or else let's say poles and equator. At poles and equator. Understood. Now, though we are considering in our calculation that Earth is a solid sphere, but in reality, it is not a perfect solid sphere. Understood. So I'm exaggerating the given situation, but it is some kind of oval.
Sir, I actually have a doubt from one of yesterday's graphs, sir.
Okay. Yes, you can ask.
Yes, sir. Could you move up a bit? Could you scroll up a bit, sir? Yes, sir.
Which one? Amog. Which one exactly? I'm not able to hear you.
Sir, there's this blue one over here, sir.
Yes.
On that, the left of that one. I'm sorry, there was some microphone problem.
Okay.
On
The
the
blue,
left, sir. On the left of that one.
this one. This one.
No, sir. If you scroll down, there was another blue one right now. So
Okay.
on the left of that one.
Okay. The left of the blue one. Yes, this one.
Yes, sir. Yes, sir. I had a doubt between that and the one on top of the blue one. You combine the two graphs now, sir. One for when G below the Earth and G above the Earth. When yes, sir.
Yes.
Over
Okay.
there, the part over there, the part which is a linear graph, that is when G is below the Earth. No, sir. You took G is equal to G naught into small r by
Yes.
capital R. Over
Yes.
there, it's with positive slopes, no, sir. Over on the left side, in the other graph, for the same thing, why is it negative, no, sir? It is.
The major
I didn't
difference is
understand that.
here it's a radius, here it's a depth. You
Okay,
see,
sir.
you are measuring depth from the top, you are measuring radius from the center. That's why you got the slopes negative.
Okay, sir. So could you tell me how that differs?
You see, here we found the expression for how it is changing with R. Clear? Where was it? Yes, this was G. Where did we write it? This was G dash M by R square. So that was uh, small r cube by small r square. Yes. So this turned out to be how much? G naught G by capital R. If you look from
Yes.
here, this turned out to be G is equal to G naught small r by capital R. Clear? G is equal to G naught small r by capital R. Now it's the same thing. That means what's the value of small r? Small r is capital R minus D. The same thing have you written here. You got it as 1 minus D by R. Now here, if you are plotting with respect
Sir.
to R, this will be of the form y is equal to minus mx plus c. That's why you'll get into slope.
Okay, sir. Understood.
That means Whenever d is equal to r, that means the value of r is equal to 0. Whenever d is equal to 0, that means the value of small r is capital R. Understood?
Yes, understood.
This is the limit, and if you move away, then it will decrease. Understood? If you want me to further extend this graph, depth becomes negative. Depth becomes negative means that is nothing but the height. Is that right?
Yes, so depth becomes negative, then that will be the height.
Height. Clear? So from there, it must be inversely proportional.
Hyperbolic.
Yes.
Yes, sir.
Understood the logic?
Yes, sir, understood.
Good. Okay. So actually,
so in that case, small r will be equal to capital R minus d, right?
Yes, always. Here from the diagram, I have taken small r is equal to capital R minus d. Depth because we measure from the top.
Okay, sir, understood.
Now here, variation in value of g at poles and equator. So actually, what was supposed to happen was that the Earth was supposed to be a solid sphere, but in fact, it is not a perfect solid sphere. There is some small variation. The thing is that it appears to be compressed. It is like appears to be oval. Understood? So exaggerating the situation. Are you getting this feel? You see?
Yes, it's not
Yes, sir.
a
It's
oblique
flattened
spheroid
into,
or something, no, sir?
it's spheroid shape.
Yeah, spheroid. The thing is that if this is the width of the diameter, I mean, if this is the radius at the equator, clear? Yeah. This, let's say this is perpendicular. This is the radius at the equator, and this is the radius at the poles. Clear? Radius at the equator and radius at the poles. Now, what is happening is that if this is a diameter, this is 2 times the radius at the equator, and this is twice that of the radius at the poles. Twice that of the radius at the poles. Now, what is, I think that is roughly, okay, roughly it is said that the radius at the poles is, I mean, the diameter at the equator 2 times RE is nearly twice that of RP plus 21 kilometer. That means if you express everything in kilometers, what is happening is that the radius at the poles, I mean, radius at the equator is slightly greater. Understood? It is slightly greater, not huge, not a huge difference, but it is nearly 21 kilometers greater. Now, what we can say is that since G is equal to Gm by R square on the surface, is that right? G is equal to Gm by R square. So if you place a block at the pole, clear, and if you place a block of mass m at the equator, so what is happening is that since radius at the poles is less than radius at the equator, what must happen? This implies the acceleration
G will be greater than
that of the equator. Not much huge, but slightly greater. You got the point?
Yes,
negligible
sir.
value, sir.
Very negligible value means uh, 9.83. Okay, whatever 9.83 value we take, that is the one
Yes, so
at
that's the
the
general.
that's the one at the poles. Clear. But
Yes, sir.
Okay, sir. Yes, sir.
coming to the equator, it will be somewhere around 9.79. So there is a 0.04
Okay,
difference in it.
Yes, sir. That difference is actually rather significant only.
Yes, this is not much significant.
Just for like for not for like this making it easier, they made it into 9.8 no, like, throughout the earth.
I didn't understand. Can you repeat?
But
To
then
make it?
not to make it complicated, I guess they just put 9.8 for every question throughout the earth,
Yes.
irrespective of the place where it is placed.
Yes, correct. So they are using the average value. Is it done?
One. Yes, sir.
Let's talk about variation in value of G due to rotation of Earth. This is something which we might not have imagined would be a reason for variation in value of G, but we know that Earth is a solid sphere. Okay, kind of a sphere. Okay, take it this way. Here also we are assuming that it's a perfect solid sphere. Now, you see, we know that Earth rotates about its axis with some angular velocity omega. Is that right?
Yes, sir.
Can we calculate the value of this angular velocity? Omega. Yes, definitely. Why?
Yes, sir.
Yes,
Yes,
sir.
sir.
Because omega is equal to 2 pi by t. This is 2 pi by 86,400 seconds or 24 hours. Is that right?
Yes, sir.
Yes, yes, sir.
So this will be radian per second. So in fact, it's a very slow value. Okay, Earth is rotating very slowly. Is it right? Because that's the speed of the Earth is twice that of the like half of that of the rate at which our hand is rotating. Is that right? In an analog clock.
Okay.
Oh, yes, sir.
Because in one day, one full day, the minute hand, our hand will make two rotations, two revolutions. But Earth is making
Yes, sir.
one. That means Earth is half that of that.
Half.
That means can
Yes,
you
sir.
visually feel it? No, you cannot feel it. Now, assume a situation that is rotating with omega. This is center. Okay. Now we always look, identify a point based on latitudes and longitudes. Is that right? So this is 0 degrees latitude, and at the poles it is 90 degrees latitude. Is that right? We say that as plus 90, we consider this as minus 90. Is that right? What is this 90 means? If you place, let's say you are talking about a point. Let's say you have placed a block of mass m over here. Clear? So if you point to its location, that will definitely make some angle theta over here. Clear? So that's theta is measured in this way. This is 0, this is plus 90, and this is minus 90. So that's how we measure the latitudes. So in this case, let's say this is, if this is rotating with omega, definitely I can say that this particle is rotating in a circle of radius some smaller. Is that right? Some radius smaller.
Yes, sir.
Now this is theta. This is the radius r. That means if this angle is theta, definitely this angle is going to be theta.
Yes, sir.
Can I say that r Kepler smaller is equal to Kepler cos theta? Is that right?
Yes, sir.
Where will be its the weight? Mg will be acting. You know that its weight mg will be acting towards the center. Yeah. So this will be the mg. In fact, you can say this will be the force mg. They are exerting force on each other. Is that okay?
Yes, sir.
So definitely there is going to be normal reaction over here. So let's say the normal reaction is this. This is the normal reaction M on the block. Clear? Any issue?
No, sir.
Now the thing is that actually if the earth was at rest, N would have balanced mg, but there is a problem now. The problem is that because earth is rotating and because this block is on a rotating surface. Clear? So if you go and stand over here, what must happen? Let's say if you go and stand over here, are you in an inertial frame or a non-inertial frame?
So we'll be in a non-inertial frame.
So we are at rest, and but we are non-inertial.
Okay.
This
Yes,
becomes
so
a non-inertial
feel that
frame.
we are at rest, but we are at non-inertial frame.
We are in non-inertial frame. So whenever we are in a non-inertial frame, what must be? Can we use the word inertia or acceleration? No, right?
No,
So,
No, sir.
So we have to use a term called pseudo force.
Yes, sir.
Yes, sir.
So where will be the pseudo force? You see, because the acceleration, original acceleration of the particle was towards the center of the circle, right? So because this was supposed to be the centripetal acceleration, here pseudo force will be away opposite of that. That means this will be mass times centripetal acceleration. I might have represented it huge, but it's not that large. Clear? Mass times centripetal acceleration.
Yes,
that means if this angle is theta, this angle is going to be theta. Clear? So if you split it into components, here if you split this into components, what we can say? Splitting this into components, I can say that this force will be MAC cos theta, and the force in this direction, that may be MAC sin theta. Now this MAC sin theta may be balanced by the friction, but we are not interested in that. We are talking about the value of G only. Now, under the influence of all these forces, the block is at equilibrium. Here, the block is at equilibrium. It is at rest. At rest means it is at equilibrium. Is that right? So at equilibrium, along radial direction. Along the radial direction, what we can say is that this is plus N plus MAC cos theta
minus mg equal to 0.
Minus mg is equal to 0. So N is equal to mg minus MAC cos theta. Now can I call this N as M times G effective? M into G minus AC cos theta. Here, what's the value of AC? Here we could have done, yeah. What's the value of AC? G effective.
So the AC will be omega square R, no, sir?
Yes.
Omega square R cos theta.
So this will be G minus AC is nothing but R omega square cos theta. But what do you know about the value of smaller? Smaller itself is Kepler cos theta. So this implies we can get that the G effective is equal to G minus of. This is Kepler omega square cos square theta. Kepler omega square cos square theta. Clear?
Yes, sir.
Now if you put theta is equal to 0. Clear? If you put theta is equal to 90 degrees at poles, what is going to happen?
Sir, 90
will be cos 90 will be 0.
It will be
so
0,
just
sir.
be G. G effective will be
cos 90 would be 0. So G effective will be equal to G.
G, sir.
G effective will be equal to G. Understood? In fact, if you want, you can call it as G naught also, but let's say it's G. Now at equator, what is happening?
Theta will be 0.
0, sir.
Theta is equal to 0 degrees.
So
this implies G effective
will be equal to
G minus
R omega square. That means the minimum possible acceleration due to gravity is at the equator only. Understood? And the maximum one is at the poles. Clear? This term r omega square is very negligible. Understood? That will be somewhere around 0.03, 0.033, something like that. Its value must be there. If you want, you can calculate the omega from the top, left top, and from you substitute with the radius of the Earth. We know that the radius of Earth is somewhere on average about 6400 kilometers. Understand the thoughts?
Yes.
Yes, sir.
Copy this.
So that mass into a centripetal is the pseudo force, right?
Yes. Are you done copying?
Yes, sir.
1 minute. Completed, sir.
Let's talk about escape speed. Now the thing is that when we are on the surface of the air, clear, uh, gravity will be pulling us backward no matter how fast you throw any object. What will happen? It will be forced to fall back. But let's say you want
Yes.
to throw a block or a ball of mass m. Clear? This is capital M from the surface of the earth, with such a speed so that it will never come back. That means VE, escape speed, that is the speed to be imparted to the projectile, so that it shall never return. So that
It escapes the Earth's gravitational field.
it shall never return by escaping Earth's gravitational field. In fact, that means if at all you see, or initially at this particular point, what's the initial energy? You see, initial energy in this case is initial kinetic energy plus initial potential energy. Is that right? Let's say the
Yes, sir.
initial kinetic energy is half mv escape square. Clear? Plus initial potential energy is nothing but how much? Minus g capital M small
Energy
m.
m by r square.
Is that right? Now what do you
Yes,
know is
sir.
Yes.
that since work done by all external agents is equal to 0, this implies change in mechanical energy will be 0. That is, initial energy will be, the final energy will be same as initial energy. Is that right? So from this, we can say that this implies, yeah, that will be how much? Final energy is equal to initial energy. Initial energy, that is equal to half mve square minus g capital M small m by r. You see, it is escaping. This is, you can compare this with some kind of, you can compare this with the electron bonded to a given atom. When, because under its, when it is revolving in its orbitals, its energy is negative. But when it can become free, when its energy, final energy, is either greater than or equal to 0. Is that right? I think you have come across that, right?
Yes.
Ionization
What,
potential.
sir?
Ionization potential.
Yes, sir.
Yes,
So
sir.
you give some energy to electron, that becomes free. So
Yes,
Yes,
sir.
sir.
do you agree when I say that by escaping, when I say escaping Earth's gravitational field, that means its final energy must be greater than or equal to 0. Do you agree?
Yes, sir.
Yes, sir.
Now final energy must be greater than or equal to 0. That means initial energy also must be greater than or equal to 0. Is that right? Let's say if I
Yes, sir,
say
because E final will be equal to E
E
initial.
Yes, sir.
initial. So for escaping, uh, E final is greater than or equal to 0. That implies, what's the final energy? That is half m VE square minus G capital M small m by R must be greater than or equal to 0. Greater than or equal to 0. So this implies I can say half m escape speed square is equal to, sorry, is greater than or equal to G capital M small m greater than or equal to G capital M small m by R. So we can cancel the value of small m. So from this, we can say that V is square must be greater than or equal to 2G,
by R.
M capital M by R. So from this, VE is equal to must be greater than or equal to under root 2G capital M by R. Understood the logic?
Yes,
So
sir.
if you calculate for this value, okay, this turns out to be, this implies VE must be greater than or equal to. How can we get the value of G capital M by R? We know that since a small g is equal to Gm by R square. So if I want the Gm by R, so I'll write it as
We
G
multiply
into
and
R.
divide by.
This is G capital M by, sorry. This will be G capital M by R. So G capital M by R. So this implies V is nothing but greater than or equal to how much? Under root 2G R. So do we know the value of G? Yes, we know it's 9.83. So we know that G is equal to 9.83 meter per second square, or we can take it as on average 9.8. But nothing is mentioned.
106,400.
Nothing is mentioned. We have to go for 9.83 only. I think that is slightly different in ISC. But as per our main syllabus, if nothing is mentioned, we have to go for 9.83. Now R is equal to 6,400 kilometers. That is 64 into 10 power 5 meter. So if you substitute everything,
Yes,
this implies the value of VE will be somewhere around
8 kilometers.
11.2.
11.2.
11.2
Yes, sir.
11.2
kilometers per second.
second. Understood? So if you throw it with this much speed, then if exactly with 11.2 roughly, then it will reach infinity with zero
E
speed.
final greater than.
Yeah, that means the final. That means it will reach infinity. The potential energy will become zero. So if you give a speed greater than this, then it will reach infinity with some excess kinetic energy. Understood?
Okay, sir. Yes,
Yes, sir.
So this is the idea behind escape speed.
So this value is mostly constant for all places on Earth, sir, or
Yes,
it differs a little bit.
slightly different, but
Not
that
very
we
significant.
ignore, not very significant.
Yes, sir.
So this is why the rockets and all that NASA, ISRO launch into space require those thrusters in the start, right? So because they have to cross this, they have to reach this escape velocity in order to go past the Earth's atmosphere, right, sir?
This one is required for sending it out of Earth's gravitational field, but
Yes,
usually
sir.
we don't
Earth's
send
not
it out.
atmosphere, gravitational field.
Whatever our scientists send the rockets, they are not with this speed. Because mostly they'll be trying to launch a satellite. So the speed
Yes, sir.
required is not this huge, it is slightly less.
That'll be
So,
orbital velocity,
that
Yes,
some 8
correct.
kilometers per second.
Yeah.
Yeah, yes, correct. But let's say you want to go into some space mission like Mars, okay, the Mars mission, and somewhere other, I mean, other than that, then you send it with this speed, minimum this speed.
Yes, sir.
Yes, sir. Sir, over here, why have we assumed the work done by external forces to be zero, sir?
Because here all other planets, okay, all other planets, they are very far from here. Understood? So their influence on the small mass is negligible.
Okay, sir, understood.
Because the small
Because
object
at
is
very
like,
great distance.
yeah, they're at very great distance. This mass m is close to the Earth. That's why we feel the effect of mass. You see, sun is also strong. Sun is pulling the mass, but do we feel the effect of sun on our body?
No, sir.
No, sir.
That's what it is, negligible. It is there. It's never zero, but it is negligible. So that's why we are assuming, though the displacement is there, the force exerted by them is negligible. So work done is negligible. In fact, you see, if you can observe here, the escape velocity is proportional to radius of the planet. If you talk about Jupiter, understood. So Jupiter is very huge compared to the Earth, right? So escape speed of Jupiter is very huge
Yes.
compared to that of the Earth. And moreover, if you are, you see, you are close to Earth, so Earth is dominating on you. So the moment Earth, you move to infinity where Earth is not able to exert any force on you, then then what will be the next dominating force on you? Sun's
The next,
gravitation.
yes, sir.
Sun.
Yes,
So what happens is that any object which is escaped from the planet must be start moving around the sun. Understood? Because now sun will be the next, I mean, dominating force. So you'll be starting to move around the sun.
Okay, sir.
okay, sir.
Is it done?
Yes, sir.
Now let's talk about Kepler's laws of planetary motion. In fact, you can apply the same logic to planets as well as satellites also, because we know planets revolve around sun, satellites revolve around planets. Understood? The same logic can be applied to both of them. But usually we stick to the idea of these planets revolving around the sun. Now here he proposed three laws. The first one of it is uh, nothing but called law of orbits. First one is called law of orbits. Now this law says that every planet, okay, every planet revolves around the sun in elliptical orbit. It says that every planet revolves around the sun in elliptical orbit such that, uh, see, I do not know the namings properly, but I think for you in 11th itself they teach you this ellipse, right? Circle and
So
parabolized.
we had to be taught.
We yet to
Okay,
be taught,
okay.
sir, but yeah, yes,
But
sir,
we
it's
have it
there.
in.
So what happens is that this ellipse is said to have two focus, 2 points called foci. One is f1, you call it as f1 and f2. The logic of ellipse is that the distance of this any point from any point P is fixed from these two focus. That means PF1 plus PF2 is constant. So that's how this shape will be formed. Now, what this law of orbit says that, what did Kepler say is that the planets revolve around the sun. Planets revolve around the sun in elliptical orbits such that sun is at one of their foci. That means they place the sun at one of their foci. Actually, sun must be white in color, but we see it as red.
That's because of refraction of scattering, basically.
Yes, because of scattering of blue light. We see it as
Yes,
red.
sir.
Yes, sir, in the atmosphere.
Yeah, that is because of atmosphere. If you go out and see it, it must appear to be white.
Pure white.
Right.
So let's say this is sun. Sun as at one of their foci, the planets revolve around the sun in elliptical orbits. Clear? Let's say we can say that this is Earth or any planet. This is sun. So this is what is said by the first law. Understood? He said that this will be ellipse, and in the future you will also learn there is something called eccentricity. So that if that eccentricity is 1, I think that will become a circle. If eccentricity is something called eccentricity is 1, that will be a circle. Here, so the logic is something like this. If this distance is a, okay, this distance is a. In fact, this is what is called major axis.
Minor axis, the other one.
Yeah, the other one is called minor axis, and the focus is said to be at a distance of EA. Here E is called eccentricity. Here E is called eccentricity. Understood? So this E is called eccentricity. If E is equal to 0, maybe, yeah, if E is 0, then that will be a circle. Understood? So each and every planet revolves around the sun in circular orbit at one of the foci. That's the law of orbit. So copy this. So every planet revolves around the sun in elliptical orbits with sun at one of their foci. So that means the circle is a special case. Circle is a special case of ellipse only. So that means all the planets, they either revolve in elliptical paths or circular paths. Is that okay?
Yes, sir.
Written copy?
1 minute, sir.
Sir, for the planets which are as in progressing away from the sun, as in going Mars, Venus, or Earth, the elliptical orbits of theirs it will become more and more elliptical, no, sir? The orbit,
Yes, they become more and more elliptical.
as in for like Mercury will have a very circular orbit.
Yes,
Then
correct.
what is eccentricity, sir? As in
Like it is something.
Sir,
Maybe
the
it's
apparent shift of, yes, sir.
here eccentricity means exactly you do not know, but here you can see this. Eccentricity is nothing but what's the distance of the focus from the center by the semi-minor axis. This A, we call it a semi-minor axis, right? So by
Okay,
A,
sir.
so it talks about how distorted it is, the ellipse. That
Okay,
means
okay.
more and more elliptical.
More electrical. Okay, okay, got it.
If E is 0, that will be circular.
Yes,
Because if the value of E is increasing, separation between the foci is increasing. That means it is becoming more and
yes,
more
sir.
elliptical.
More and more electrical, and yes, got it.
Done.
Now the next one is what is called law of areas, because it talks about the area swept. So this one is called law of areas. Let's say the particle is moving. Okay, the particle is moving in this elliptical orbit with sun at one of their foci. Let's say this is the sun. This is sun. Clear? Now, assume that the particle is somewhere over here. Okay, sorry, no, not the particle, the planet. The planet is somewhere over here. Clear? The planet is somewhere over here. Let's say this was at a time t, at some random time t. The planet was over here. Let's say in this additional small time dt or delta t, what it will happen? It will cover some distance, right? It will be definitely covering some distance. Now, what we know is that at any instant of time, the velocity must always be tangential. Is that right?
Yes, sir.
The velocity must
Yes,
be
sir.
tangential, always tangential to the curved path. So that means that this is the radius, this is the tangent. So they're perpendicular. Now what is happening is that let's say the particle has have come to a new position. Clear? So the speed is changing. So let's say this is v. I'll assume that the speed has increased dv, v plus delta v. Why should I assume that it is decreasing? Now let's say at that instant the radius is r. At that instant the radius is r. Now let's say it has reached to a new point of a radius r plus dr. I know in this diagram it is decreasing, but still, whenever we say that something is changing, then we must assume that it is increasing. That means definitely, can I say that there is a small change in displacement?
Yes, sir.
Yes, sir.
I mean to say, can I say that it has covered some area over here? Yes, definitely it has covered some
Yes,
Yes,
area.
sir.
It has definitely covered some area. Now, how can we calculate this area? We know from vectors. We know from vectors that uh, okay, let's call this as r initial. This is slightly changed. Okay, that is, let's say this is r final. Clear? So definitely there is some change in position. This was the original position vector. This was the original position vector. Now this is going to be the final position vector. This is the initial position vector. This is the final position vector. So can I assume this as my change in position vector? This is my change in position.
Yes,
Is
sir.
that right? This is my change in position. That will be how much? Dr bar. That's my change in position, dr bar. Another thing is that from vectors, if you remember, we know that if this is A bar, this is B bar. If we construct a parallelogram using A bar and B bar, so we know that A bar cross B bar represents the
area of the parallelogram.
Parallelogram.
Yes, sir.
So that means if you want to talk about a triangle, if you want to talk about the area formed by triangle,
half of A bar cross B bar.
Yes, sir.
A bar cross B bar. So that was the
Half
area,
of
right?
the area of parallelogram.
Half of area
Yes.
of parallelogram.
So this triangle, area of the triangle delta will be equal to half A bar cross B bar.
Yes.
For that of the triangle. Clear? This is for the triangle, and for the parallelogram, that was A bar cross B bar. Clear? Magnitude. Now here also the same logic, the small area swept can I write as half into R bar cross dr bar. Half into R bar cross dr bar.
Yes, sir.
Oh, yes, sir.
Is that right? Yes. Now what do you know about dr bar? Since dr bar is equal to V bar times dt, do you agree? Displacement in the tangential direction is tangential velocity times the small time taken. This was
Yes, sir.
at a time t. You see, it was here at a time t, and it is at the new position at a time t plus delta t. This is a time t, and this is a time t plus delta t. So in that small dt time, it has traveled over here, or else we know v is equal to dr bar by dt. That's what we can say. Clear? If not, I'll differentiate this and say that this is v bar. Is that okay? So from this dA, can we say that this will be dA is equal to half into R bar cross dr bar by dt. So that is V bar times dt. Bring this over here. This will be dA by dt is equal to half into R bar cross V bar. R bar cross V bar. Now what we'll do is that let's multiply with mass on both sides. Understood? Let's multiply with mass on both sides. Is that okay?
Yes, sir.
So multiply by mass on both sides. This will be m times, or else this implies I'll say dA by dt is equal to, I'll write it as 1 by 2m times R bar cross mv bar. Now
That
this
will
is
be
1 by,
angular momentum.
yes, very good. This will be R bar cross P bar. So that will be how much? R bar cross P bar is nothing but L bar. So this is L bar by 2m. So we found that the time rate of change of aerial velocity dA by dt, I think this must be magnitude wise. I did not put mod over here. So everywhere you take mod. Okay, if you want to talk about the only the areas magnitude. So this is area, because we usually consider area as a vector. So that's why I did not do it. But if you want, you can put a mod over here. So everywhere will be a mod. So this will be magnitude of L bar by 2m. So dA by dt is L bar magnitude by 2m, or L by 2m. Now look here, is there any torque acting on the particle? The force, centripetal force. If at all there is any force, that will be the nothing but the centripetal force. Is that right? Now this is the centripetal force always. Centripetal force and radius, they are perpendicular. So what can you say that since centripetal force is perpendicular to the displacement dr, sorry, not the displacement. Here, centripetal force and the radius. Centripetal force is along with the force. Clear? So what we can say is that since Fc bar is anti-parallel to dr bar, torque due to centripetal force. This implies torque due to centripetal force will be how much? 0. If torque due to centripetal force means angular momentum of the center must be how much? It must be constant. Delta L bar must be equal to 0. This implies L initial is equal to L bar, and that is constant. Clear? So that means this L by 2m is constant. That means what is it saying? It is saying that the rate at which the area is changing. That means that is what is called time rate of change of area. This is what is called aerial velocity. aerial velocity is constant. That means that is the planets cover equal areas in equal intervals of time. That is the planets cover equal areas in equal intervals of time. Equal intervals of time. So copy till here. We'll continue the discussion tomorrow.
Thank you, sir.
So just wait for 1 minute, sir. Yes,
Yeah,
sir.
sure.
Thank you, sir.